Hello everyone, I'm Norman Wildberger. We are currently investigating what I consider to be the most important and fundamental problem in mathematics, which is how to model the continuum. This has a lot of aspects. Today we're talking about the question in the time of the beginnings of the European mathematical tradition. In particular, how the development of calculus stimulated various competing ideas about the continuum. Our hero today is a Flemish engineer and scientist named Simon Stevin, who lived from 1548 to 1620. And in 1585 he published a little booklet called De Tiende, which I believe is Dutch for the art of tenths. So Stevin believed that Dutch was a particularly effective language for communicating mathematics. Most everybody else at that time was writing in Latin. He was a very original thinker who had all kinds of other interesting ideas and contributions, but we're interested primarily in this pamphlet of his, in which he basically lays out a case that the Hindu-Arabic decimal notation was the best and simplest way of actually doing numerical calculations. So the Hindu-Arabic system had been slowly introduced into Europe in the last few hundred years before his time. So for example, Fibonacci, Leonardo of Pisa, wrote an influential book 300 or 400 years before advocating the Hindu-Arabic decimal notation. So Stevin says we should think about this decimal notation and arithmetic as an replacement for arithmetic with fractions, and allowing us all to calculate things like square roots and other what we would now call transcendental quantities. So for example, instead of having 3/4, he would write something like 0.75 in the Hindu-Arabic notation, where this is the ones column, this is the tens column, hundreds column, and this is the 1/10ths column, this is the 100ths column, and so on. And 2/3, he recognized, was a repeating decimal, 0.6666, and so on. His actual notation differed a little bit from our modern one. So he had these various auxiliary numbers that showed where the position of the various digits was. All right, so basically his idea was that if we work with decimals, then basically everything should reduce to just natural number arithmetic. As most young students know, kids in primary school, learning arithmetic with fractions and understanding it is a pretty sizable accomplishment. And so he was advocating a more simplified, practical way of doing things. But along the way, he also pointed towards important future developments, and his little booklet turned out to be exceedingly influential in steering most mathematicians after that time in the direction of decimal numbers to extend their number arithmetic. Alright, so Stevin showed how to add, subtract, multiply, and divide with these decimal numbers. So for example, here is the sum of two decimals, and we know to line things up so that the ones and the 1/10ths and the 100ths and so on are all above each other. And then we add starting from the right and carrying, just as we were doing with ordinary Hindu-Arabic natural numbers, except that we have to be a little bit aware that there's going to be a decimal point in the answer. Subtraction is much the same, and multiplication is again also the same. The only main difference is that you have to be conscious of where the decimal point is at all times. But otherwise, really, the multiplication of 5.63 times 1.4 is not that much different from multiplying 563 times 14. With division, we can also do long division. So here's 14.27 divided by 3.5. The first digit is how many times 3.5 goes into 14.27, and maybe 4 times. 4 times this is 14.0. We subtract. Then we ask how many times does 3.5 fit into here? And the answer is 0.7 times. 0.7 times this is 0.245. Subtract and keep going and so on. And typically what happens here is that we don't actually stop. We keep on going, and because 4.77 over 3.5 is really the same as 477 over 350, he knew that the result of such a division is going to be a repeating decimal. And he also knew that, okay, we can deal with fractions this way and arithmetic with them, but we can also calculate some other things, like maybe root 2 or pi, giving an unbounded decimal expansion that was probably non-repeating. So at that time, of course, the ancient Greeks knew that there was no fraction whose square was 2, but pi was probably suspected to be not rational, but it wasn't known until later. Okay, and I put these numbers in quotes here because it's going to be an issue for us what exactly these things are, and the actual definitions of pi and root 2 are really part of this whole story. Okay, the question of what are we actually talking about here. In any case, Stevin had a relatively consistent framework for doing arithmetic that allowed us to do familiar fractional arithmetic and also go beyond. But Stevin did more. He also outlined a strategy for solving polynomial equations. And the strategy might be described as a divide and conquer strategy, and it will probably be familiar to those of you who've watched famous math problem 17. I talk about essentially the same idea at some point in there when I'm talking about calculating the square root of 19. So to give an illustration, suppose we're interested in solving this cubic equation, x cubed minus 3x plus 1 equals 0. So one thing we might do is to graph this function, so as a function of x, graph a few points, join the points up, get an idea, and the picture suggests that there's going to be 3 solutions, one somewhere near minus 2, one somewhere between 0 and 1, and another between 1 and 2. And in fact, one can calculate that these 3 values are approximately given with these numerical decimal values. So let me show you how Stevin would have tackled finding such a root by his method. So let's look at x3. Let's try to find the biggest root here, the one that's furthest to the right. The picture shows that it should somewhere be between 1 and 2. And so what we do is we first check that the function's value at 1 is minus 1. So if you plug 1 into here, you get minus 1. And if you plug 2 in here, you get 8 minus 6 plus 1, that's 3. So the function's value at 1 is minus 1. The value at 2 is 3. So Stevin argues that it's somewhere in between there. This function is changing continuously. So somewhere in between x equals 1 and x equals 2, it should be crossing the x-axis. In other words, it should have the value 0. Okay, so then his basic idea is to say, all right, let's have a look at this interval between 1 and 2. Let's take a good look at it by expanding it or dividing it by 10. We're going to divide it into 10 pieces, make a scale. So 1.0 here and 2.0 here. The endpoints, we've blown it up. And now you can see 1.1, 1.2, 1.3, 1.4, 1.5, all the way up to 1.9, 2.0. And now we can evaluate the function at each one of these intermediate values. So f at 1.1, just plug 1.1 in here and calculate, you get minus 0.969. F of 1.2 is minus 0.872. Here's f of 1.3, f of 1.4, f of 1.5. We see that the values are increasing. They're all negative, but they're increasing at this point. But then at f of 1.6, we get a positive value of 0.296. So somewhere between 1.5, which is here, and 1.6, which is here, somewhere in here, the function is jumping from negative to positive. So it's going from some value down here to some value up here. So it's doing something like this. And that means that the 0 that we're looking for, x3, is somewhere between 1.5 and 1.6. And you can see, in fact, what we're really doing here is calculating that first decimal to be 0.5. So we know that x3 now starts with decimal 1.5. All right, and then he would repeat. And then we'd say, okay, now we take this interval 1.5 to 1.6. We divide it up into 10 pieces corresponding to the various values of the 100th digit. We run through the function's values at each one of those and decide, where there is a jump from negative to positive, and that's going to tell us that the next value is 3. And we can keep going like that by essentially blowing up all these smaller intervals and checking values of the functions. Where does it go from negative to positive? So Stebbins would have, with his method, been able to calculate a 0 or an approximate 0 like this to this polynomial equation. And this is a very powerful and general technique that's in some sense, more general than any particular method for solving a quadratic or solving a cubic. It's a very general method that we can apply to all kinds of functions or curves or polynomials. In fact, the method really these days is more usually associated with Cauchy's work. So several hundred years later, Cauchy, a very important 19th century mathematician who was one of the founders of modern analysis, used essentially this idea to develop what's now called the intermediate value theorem, which is a result that most students learn. They are often wondering why they learn it because it seems sort of just obvious. Namely that if a function has a negative value at one point and a positive value at some nearby point, and it's continuous, then at some intermediate point it's got to take the value 0. But it turns out that that seemingly obvious property or theorem really depends very crucially on our understanding of the continuum. This wasn't really properly appreciated in Stebbins' time, but in the 19th century it became clearer. In any case, Stebbins was a very important pioneer in developing this understanding, and it's a very important sort of idea of finding solutions to polynomial equations. It is often claimed that Simon Stebbins was sort of the father of the theory of real numbers, but I think this is a dubious claim because Stebbins did not really tackle the definition of infinite decimals, and he left their arithmetic somewhat open. So Stebbins was an engineer and very practically minded fellow. And his aim in writing this pamphlet was actually to introduce this very practical method to a wide range of people, and he was very successful at that. He wasn't really proposing a theory of infinite decimals and with all the subtleties of trying to deal with infinite sequences, whatever those are. That whole bag of worms sort of came later. In fact, Stebbins' work, in my opinion, has in fact 2 serious logical flaws. And I think it's important that we have a look at them. So the first flaw is that in order to establish fraction arithmetic, which is what he wants to do via decimals, you really need to show how to add and multiply repeating decimals. So it's not enough to explain to someone how you add and subtract and multiply finite decimals. Decimals that are finite in extent and then they end. That's not enough because when you're working with fractions and you convert your typical fraction into a decimal, well, chances are you're going to get a repeated decimal out of that. And so if you want to mimic an operation like 2 over 7 plus 8 over 11 equals 78 over 77, if you want to mimic that over in decimal land, you have to know more than just being able to add or multiply finite decimals. You have to know how to deal with these repeating decimals. That is quite a lot more tricky, in fact. It's not insurmountable, and it's a very good exercise to do. You'll probably find that addition, if you think about it, is not too hard, but you have to be a little bit careful. But multiplication starts getting quite a lot trickier. Right, so what you have to do is you have to, you've got this repeating decimal, so 2 over 7 happens to be this one here, 285,714, and then it repeats 285,714, and so on. And 8 over 11 is 0.72727272. Now, how are you going to add these things? There's no place on the right hand where things stop. That's how you usually add decimals, is you start on the right and work your way over to the left, carrying all the time. Here you're not in a position to do that, unfortunately. So what you have to do is to start on the left instead and work your way to the right, exactly the opposite of what you're doing ordinarily. And as you work your way to the right, well, you're often going to get carries, and then these carries are going to change the results that you've already got. So you have to work in a kind of a temporary fashion, being prepared to rub out and change some of your computations as further digits are revealed. To say precisely how you're going to do that, in other words, to train someone to do that, is not entirely trivial. The point is that Steven did not do that, and so really he does not have an arithmetic of fractions in his decimal system. And you might like to think about subtraction and division. Those are even more challenging. If you think about how you're going to divide this decimal by this decimal. Turns out to be a lot easier if you convert them back into fractions and do the arithmetic over there, if you want to be precise. Of course, Steven was an engineer, and he would very likely have said, well, that's a true objection, Norman, but really, why don't we just chop these things off at some convenient point, okay? Once we've got 10 decimal places, that's good enough for any practical purposes. We'll just chop them off. The repeating decimals become finite decimals, and then we just perform the operations as I've indicated. So as long as you're working in an approximate or engineering kind of framework, this is a flaw that's not visible or one that you don't care about. The other flaw I want to point out is a more subtle one. It's that Steven's method for solving polynomial equations that we saw, where he iterates, dividing the interval in question into tenths, and then looking at subintervals and blowing them up and dividing them into tenths and so on, getting individual digits one at a time, is at every stage only an approximate procedure. At any stage, we've just gotten a certain ways into this decimal. And it does not establish the existence of solutions. Okay? So what we're getting at every stage is that if a solution exists, then it's somewhere in between here and here. So for example, if we found that the third decimal is a 5, then we know that the number, well, is somewhere between having a third decimal 5 and a third decimal 6. It's giving us a range of values or an interval. But it's not telling us anything about the existence of a limiting value to this procedure that we're doing. Maybe there's a rational number which is a limiting value, but maybe there isn't. Okay, this flaw is shared by most subsequent theories of real numbers, namely that the objects of study are not first clearly identified. Okay, so let me say this in some other words. It's a very subtle business, but very important. So before we start computing and studying something like, say, root 2, or the largest solution of x cubed minus 3x plus 1 equals 0, or pi, or e, or log 10, or gamma, or maybe many other things, we really ought, logically, to first define what we're talking about. So first we should define these objects, and then we're in a position to compute them and study them. So if we assume already, to begin with, that these objects exist, then we've already made a fantasy land kind of jump over the river. Right? It's not really allowed. So it's easy to fall into this trap. Okay? To this idea, for example, that if you have a circle, that the length of a circle is a well-defined notion. It's not at all clear that the length of the circle is a well-defined notion. It's not clear that the length of a line segment is a well-defined notion mathematically. It's not clear that various series that perhaps define these quantities actually result in a well-defined object. Okay, so that's a problem that Steven shares with many other theories of real numbers, and it's something that in discussions of this topic, which I'm sure you'll be happy to get yourself involved, it's really important that we don't let people just get away with assuming that the words already have a preordained meaning. Okay? If you want to talk about the square root of 2, that's fine, but first you define what it is exactly that you're talking about. And if you say, well, it's the length of such and such, then you have to define, first of all, what you mean by length. And you might very well find yourself going back to Archimedes and realizing that the length of a circle is not such an easy thing to get your finger on. That it's safer to say that if we approximate the circle with line segments, or polygonal thing, then the combined perimeter is somewhere between this value and this value. And not assume that there's an intermediate value that actually the length actually is. Okay. With the development of calculus in the 17th century, the nature of the continuum became a very important and a widely discussed topic. Because in calculus, first of all, we're interested often in assigning numbers, finding numbers that measure physical quantities of interest. Perhaps the length of a curve, or the area in some closed curve, or perhaps the volume of some region in space. And the question arose, well, are these concepts really well-defined concepts? Does it make sense to talk about the length of a curve? These days, students are never taught to question this. They don't realize that in the 17th, 18th century, this kind of question caused a lot of people major headaches. It wasn't entirely obvious that the length of a curve was a well-defined notion. But there was another aspect of the continuum question that arose in the very foundations of calculus, and that's this issue of infinitesimals. Okay? This is a subject that was very close to Leibniz and Newton, and we can see it even embodied in Leibniz's notation for both the derivative and the integral. So Leibniz's notation for the derivative of a function f prime of x is dy over dx. And his notation for an integral from a to b of f of x dx. And in many of his workings, this dx and this dy were thought to be very, very small quantities. In fact, more than just very, very small, they were often considered to be infinitesimal quantities. So these were values, non-zero values, which however were smaller than any given rational value. And so there's now a suggestion that perhaps the number line of the continuum might have infinitesimal aspects. If we look at a number line like this, not only do we have fractional values, but maybe there's actually infinitesimal values which are smaller than any fraction, but still non-zero, hovering somewhere to the right in some sense to zero. It's very hard for us to say whether, what we think about that, isn't it? Because, you look at this and you say, well, how am I going to think about it? Is it right to include infinitesimals? Well, it was certainly an effective tool for Leibniz and for Newton and for many practitioners of calculus after them. So, for example, here's a function, here's a point, here's a tangent. Well, then the slope of the tangent, the derivative at this point, can be defined as the ratio between this displacement and this displacement. And Leibniz liked to think in terms of not just small quantities, which are these days usually called delta x and delta y, but actually in terms of infinitesimal ones. And of course, here's the idea of an integral. Something like this was regarded by Cavalieri and others as really an infinite sum involving a lot of rectangles, which in fact are infinitely thin. Okay, so this integral is really a stretched out s, standing for sum, so it's a sum from a to b, and we're adding up values which are areas of small rectangles. The function's value being the height, and this infinitesimal width down there in the base. And so you have to think of these rectangles as being really infinitesimally thin, and there's an infinite number of them stacked up. Well, does that actually mean anything? Is it correct? People debated this, but it was undeniable that the mathematics that they were able to develop with these ideas was very effective. Work with infinitesimals was in this spirit here. For example, suppose you have function y equals x squared, call that f of x. Then one way of calculating the derivative would be to calculate the function at x plus dx, where dx is just an infinitesimal small number. And then subtract the value at x. Well, x plus dx squared, that's f of x plus dx, while f of x is minus x squared. And if you expand this out and subtract x squared, you get 2x dx plus dx squared. And if dx is infinitesimally small, then dx squared is 0, essentially. Okay? And so then you just get that this difference, which is dy, is 2x dx, which allows you to solve for dy over dx being 2x, and that's how you get the derivative. So manipulations like this were often made a lot easier by assuming that these small increments were actually infinitesimal increments, and this became a very powerful technique in lots of physical problems. So naturally, there's the question, do infinitesimals really exist? Should we augment our understanding of the continuum to include infinitesimals? That is, in some sense, still something of an open question these days. So a natural question that arose at that time was, should we allow infinitesimals as elements of the number line? And if so, how do we incorporate them properly into an arithmetic? A related kind of question is having to do with the nature of curves, which to the 17th and 18th century mathematician was far from obvious. Okay. So a natural question, for example, is, what is a curve? How do we think about what a curve actually is? And Leibniz and others thought that perhaps we should think about a curve as being a sequence of infinitesimal line segments. So here's a sort of simplified model. Here's a different curve, but you're thinking of it as the small line segment here, and then followed by another line segment, followed by another line segment. So very much the way a modern computer program might draw a curve if you expand it. But with the idea that these line segments are actually infinitesimally short. If they were a finite extent, then you would see them, and then there would be actual corners. So they thought, well, maybe we should think about infinitesimal line segments all sort of merged together to form the curve. This is not the way people think about them nowadays. Nowadays, if I asked most students what is a curve, they would probably say it's a set of points, which is, in fact, also a kind of infinitesimal picture, isn't it? So if you think of it as a set of points, then what you have is a whole bunch of points stacked one beside each other in some sense. Each of them is actually also infinitesimal in the sense of having 0 diameter. A point is infinitesimally small. So this pointillist view of a curve that we now have is in fact not so evidently superior to Leibniz's view of a curve as a bunch of infinitesimal line segments somehow strung together. So in some sense this goes back to the paradox of Zeno and to what extent can we subdivide and infinitely subdivide things to make things infinitely small. Archimedes thought a lot about infinitesimal segments, balancing them up to provide motivation for some of his lovely formulas. Mercator was one of the first people to actually introduce the idea of infinitesimal. Cavalieri worked a lot with infinitesimal strips forming areas. The Bernoullis were very keen practitioners of infinitesimal analysis. And most physicists and many engineers in the centuries since then naturally use infinitesimals, very powerful method. Euler, Lagrange, Cauchy even, I didn't mention. Even up to the 20th century where after a long period of sort of decay, infinitesimals got a major revitalization with so-called non-standard analysis. And Kiesler was even able to write a very nice calculus text based purely on an infinitesimal approach using non-standard analysis. So although many found infinitesimals useful, there were others who objected. who said that, wait a minute, this doesn't make sense. What exactly are we talking about here? And prominently there was a fellow called Bishop Berkeley whose attacks against infinitesimals were particularly important, and started motivating people like Euler and Lagrange to maybe find a better way of founding the calculus, which in my view they were ultimately able to do, but that's quite a different story. So you can see that the calculus did really generate quite a lot of discussion about the nature of the continuum. A lot of these developments still sort of cast their shadow even on a modern calculus course. So these days, controversy over infinitesimals has morphed into rather a debate about the role of differentials. Let me just give you one example here. So if you have a function, say f of xy, then sometimes it's useful to consider the differential of f, df. And then there's this formula that says df equals df dx dx plus df dy dy. Okay, and these are the partial derivatives of the function f with respect to x and y, and dx and dy are differentials, which are probably best thought of as very, very small changes in x and y. Actually, better think of them as infinitesimal changes in x and y. This kind of formula is even today very common in calculus texts and very useful. And there are a lot of situations, if you're teaching calculus, where you would like to just present things in terms of differentials because things are easier. And so there's always this underlying question of, well, what exactly are we talking about? And most educators who have worked with calculus have wrestled to some extent with this kind of question. Now, another very interesting development that came out from calculus that sort of challenged ideas of the continuum were complex numbers. All right, so complex numbers were numbers of the form a plus bi, where a and b were ordinary numbers, but where this I was some kind of newfangled number whose main property is that I squared equals minus 1. Now, we all know that there is no such number that squares to minus 1, but we're here declaring that, yes, there is, and we're calling it I. And it turns out that you can do a sensible arithmetic with this kind of number, and that it turns out to be very useful. And eventually people realized that it was profitable to visualize this in a plane, say the xy plane, where the a coordinate is in this direction and the b coordinate is in this direction. So the complex number a plus bi is identified with a point a, b in the plane. Now, there's an interesting sort of historical aspect here. So complex numbers had been around before the beginnings of calculus, and Descartes called a the real part of the complex number and b the imaginary part of the complex number. So he was the one to introduce this terminology. And from his point of view, you can see that's quite reasonable. You know, this is sort of like an ordinary number that's familiar and just like all the numbers we were used to doing arithmetic with, while this bi thing is the weird sort of imaginary new thing. So he called this the real part and this the imaginary part. And it's really at this point here that the so-called real numbers get introduced terminology-wise into mathematics. But one should make clear that Descartes was not talking about these things as real numbers in the same sense as we are now. Nowadays, we have given a lot more meaning to this. This is some kind of sophisticated number system that allows infinite processes to have limits and so on. Descartes was not thinking at all about that. He was just thinking about that part and that part of an ordinary complex number, like 3 plus 4i. While complex numbers originally caused people a lot of confusion because they didn't understand how they should think about the nature of these new kinds of objects, eventually people realized that you could work with them in a purely formal way and not worry too much about what they really were. So ultimately, a kind of symbolic working replaced the idea of having to define them in terms of other things. And at the end of the 19th century, a more algebraic approach to what are now called fields and field extensions was developed. And it was then realized that one way of thinking about this very general kind of way of how we make complex numbers is that we start with polynomials. So we start with just polynomials with rational coefficients. And what we do is we mod out by an ideal, okay? And roughly what that means is that basically we just work with the algebra of polynomials in the usual fashion, but we agree that this particular combination, x squared plus 1, amounts to 0. So whenever you have x squared plus 1, you can replace it with 0, which is the same as to say that x squared is equal to minus 1. Whenever there's an x squared in some polynomial, you can replace the x squared with minus 1. Okay, well in that case you get the complex numbers are then those things of the form a plus bx, where x is playing the role of I. But this algebraic kind of orientation allows us to do similar but quite different things. So, for example, we can create fields or field extensions of the rationals where we have square roots of 2. So what we do is we play a similar game. We consider rationals, but we think about the relation x squared equals 2 instead of the relation x squared equals minus 1. Right, if we do that, then we can work just with polynomials of the form a plus bx, and whenever we have an x times x, we replace it with 2. And then the crucial thing that you have to check is that you can actually do the arithmetic properly, and the most trickiest thing here is to figure out how to divide. Okay, so the way you divide in this kind of field is the same way you divide in the complex numbers. You basically multiply top and bottom by the conjugate of the bottom. So if you multiply a plus bx by a minus bx, then this difference of squares becomes a squared minus 2b squared. And the numerator is a minus bx. And conveniently, this thing here is never 0 because there's no rational number, a over b, so that a squared over b squared equals 2. That's what makes it work. Okay, and you could call this then q adjoins square root of 2. Or in the same language here, you're modding out the ring of polynomials q of x by this ideal x squared minus 2. And this is a very flexible way of generating algebraic extensions in which our arithmetic is expanded. So in the ordinary rationals, there's no object whose square is 2, but in this concocted field, well, there is an object whose square is 2 because we've built it in. But the point is we built it in a consistent way so that the arithmetic is still consistent with the underlying arithmetic of the rational numbers. So if you're in a situation where you need to have a square root of 2 around, this extension field is the domain in which you probably want to be working. So these new extension fields that were introduced, in the 19th century provided some challenges to our notions of the continuum, because there's an obvious divergence between the geometry of the extension fields and the usual number line. In particular, something like q root 2 is actually two-dimensional in a natural sense. It's naturally modeled by a plane of points, just like the complex numbers is, rather than a line. And when you do more sophisticated things, when you say want to have a square root of 2 and a square root of 3 around, then you find out that the algebra forces you into four-dimensional space. And if you want more square roots or want to throw in some cube roots and so on, well, you get Galois theory and it becomes quite complicated algebraically. It becomes very complicated. So there's an increasing arithmetical complexity as we add more square roots, cube roots, etc. So we are able to extend the continuum to allow us to solve these polynomials algebraically. But this is not really the same as finding the numbers square root of 2 or cube root of 2 or square root of 3 on the number line. Okay? It's different from that. It's very different from finding a number whose decimal expansion is 1.414 blah 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 on the number line and saying, aha, that's where square root of 2 is. The square roots of 2 that we construct here are algebraic and they're somehow independent of the number line. And that's just a fact of the way things are. But it makes this subject harder for students to appreciate because students who have learned a little bit of undergraduate mathematics know about the algebraic construction of root 2, and they often get this algebraic construction mixed up with the analytic root 2, which they believe is on the analytic line. Okay? The algebraic construction is not a replacement for the square root of 2 in decimal form, which in my view has a very problematic existence. Another interesting and perhaps disconcerting possibility is that once we start thinking in terms of fields, we realize that there are also finite fields floating around. There are finite fields, say f sub p, for any prime p, which raises the perhaps unnerving question, might it be that the physical world is based not on the rational numbers or some extension of the rational numbers, but maybe on some field, some finite field f sub p for some very large prime p. The arithmetic in f sub p for p very large starts to approximate the arithmetic for the rational numbers, in a certain way at least. And it's not at all clear what our physical reality will end up being. It's certainly possible that in fact the universe is modeled on some f sub p for some huge p. It's possible. We don't know. Okay, so these are some of the challenges that arose out of 17th, 18th, 19th century thinking about calculus and the applications of decimals, Hindu-Arabic notation, to the problem of how do we model a continuum. And it all came sort of to a head in the late 19th century, where finally, after a lot of controversy, it was established that the continuum was the real number line. Falsely established, in my view. This was mostly the work of Richard Dedekind, who, in my view, instituted the greatest sleight of hand in the history of mathematics. I'm going to tell you about that next time, where we're going to wrap up this particular problem, talk about Dedekind cuts, and talk about other constructions of the real numbers, and move to 20th century confrontation with the theory of computation. Right. This is really the core problem today, is that the ideal world of pure mathematics and the world of computer science are growing increasingly further apart in different directions because of the, in my view, misguided understanding of the real number line that we currently have. So next time, very interesting, we're going to address a lot of the difficulties of the modern view of the continuum, and I want to show you that this is still a very open problem and a very important one. So I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.